So we are spending a second day on electrochemistry, and what we're going to spend some time on is these tables of reduction potentials and investigating the chemistry in there. And I'd say about a year ago, I put 2 nails in water, right? One's getting all rusty looking, right? And the other one's, just the opposite. So I don't know if you've ever spent time, I doubt it, but you should. If you haven't, do some real manual labor, work on a roof, fence, whatever. If you use the wrong bloody nails, your job is done and it's going to fall apart in a year or two. So they use something, but nails, how about something more expensive, right? In the Navy, has billion-dollar destroyers or this ship, right? You got to stop this rust from happening. You have to make those ships out of iron, so how are you going to stop them from rusting? Electrochemistry is the answer. And by the end of the hour, we'll show you exactly how they do this and how it works. Okay? So that's coming up. So let's get started here. First, we're going to see if we can calculate. Some homework has getting equilibrium constants from these E0 potentials from our cells. Okay? So let's see if we can not only do the math, but make sure we know how to use the equation. What is this? Little n. We had it before on the quiz, moles of electrons. Here we had little n on the quiz. It looks like the exact same little n, and it's moles of electrons, but right, you can do a little bit of work or you can do a lot of work, right? So that little n, moles of electrons, that just depends on how much stuff reacted or was produced, right? So that little n is going to change on you all the time for work, but not for an equilibrium constant, right? That little n has to be a constant number because there's only one equilibrium constant for a reaction, and it's still moles of electrons. Can you imagine how are they going to get that little n then? I'll give you a hint. How do you get these overall cell reactions? You add up the half reactions. Okay. So here's our overall cell reaction. And you can do products over reactants and get your K, right? Concentrations of products over reactants. But in getting that overall reaction, what canceled? The electrons. How many electrons canceled? Maybe, I don't know. Maybe you had to multiply this one through by 2 and this one through by 3. It really doesn't matter, but let's say 6 electrons canceled. Well, then my little n's going to be 6. So it's just the electrons that cancel in the equation. So it's still moles of electrons, but it's kind of confusing because down here it's the same n, right? You probably should have used a different little symbol, but okay. Now in the quiz, right, I give you all the equations and everything. This is the only equation I give you. And the homework question says, hey, what's the equilibrium constant? So we have to know how to manipulate that to solve for K. So Mari, what would you do first? Right? We want to start here. How would you solve for K? What could you do first? Yeah, so we'll put in, good. So we'll put in numbers for all this stuff. Okay? But then you have to manipulate this thing and solve for K. So Eric, we have numbers for everything. What are you going to do?
So multiplied by n divided by
You hear what he's doing? That diagonal thing, right? Do that. Man, we're doing that for 2 semesters. He said E cell, brought that up there, times the n, divided by the 0.0592. Really close, right? Remember, we did this before. We got rid of log. How do we do that? Raise it to the 10. When do you raise it to the little e? Oh man, you guys are on. They're showing off for you, sister. So we're going to raise both sides to the 10. So what? 10 to the E0 cell times n over 0.0592 equal 10 But those are inverse functions, so they're gone, right? So that's just K. Okay, so know how to manipulate that and solve for K. So here's all of our electrochemical equations that we've got so far. Okay, first question. All spontaneous or naturally, now I changed some of this, as you know. See, they get these little outline books. They spend big bucks, right, at the beginning of the semester for these things. And then I end up changing it 10 minutes before class. Anyway, this is one of those occasions, just to give you a heads up. All spontaneous, I'm picking on summer. All spontaneous or naturally occurring cell reactions have E0 cell values that are, now there's the only, what did you say? To me, this is the only one I memorize. That Gibbs energy. They made a big deal out of this. Remember, delta G was what for natural processes? Delta G was negative. That's the only thing you got to remember. So that's what I like about chemistry. It minimizes the things you got to memorize. You got to memorize that. Delta G is negative for spontaneous things. Well, if delta G is negative, well, N is just moles of electrons. That can never be positive. Oh, sorry, that can never be negative. That's always going to be a positive number. F is that Faraday's constant, right? E0 cell, if N and F are positive, E0 cell would have to be what for delta G to be negative? Positive. You got a negative sign in there, right? If E0 cell is negative, it's going to cancel with this guy, and they're going to get positive, and it ain't going to work, right? So E0 cell has to be positive. Then you have a positive times a positive times a positive times a negative sign, negative. So the answer to this first question is positive. Long story short, yeah. What equations, so we've got a bunch of equations here. Alyssa, which one of these is probably the easiest way to get E0 cell? Yeah, you agree with her? I think so too. That's probably the easiest way. Okay, so that's going to be our game plan. Now, how do you get these values, Maria, to substitute into that equation that Alyssa picked? From the chart, right? And in fact, we've got some down here. There's a chart. What do we call the chart? Standard reduction potentials. Right? Okay. So that's how we're going to get, how do you tell the difference, though, between cathode and anode? Right? We're looking in here, going to pick these numbers. Right? Anode is producing the electrons, right? We can do it that way, but we never really cared. Do you remember why we never cared? I mean, we should care, but we never really did because the math didn't care. We just picked these E0s that were the most, do you remember this? Back up to this one. It doesn't have to be an overall cell. It could be a half reaction. You pick those E0 values that are the most what? And they're going to be the most natural, most positive. And that's what we did. We picked half reactions and added them up. Do you remember this? We picked half reactions and added them up. Well, we have to flip this one. If we flip this one, what do we do over here? Flip the sign. And remember, that's the game we played to get the most positive overall E0 cell. Why? Because the most positive means the most natural, the most aggressive, the most, I mean, you can't really stop them all from happening, but it'll be the most aggressive. Happen predominantly. Okay, so what is the question? Whoa. Okay, here we are. How do we get values? From the tables, you guys kind of said. And then if you remember, if you have to flip a reaction, you flip the sign, just like you said. And how about this one? We kind of already answered it, but the more everybody positive. So this is, again, I changed it from what's in your outline. But the point is the same. The more positive values of E0 cathode, E0 anode, and E0 cell are the more spontaneous or aggressive. I like the word aggressive because dang, you can't really stop a lot of this stuff from happening. And we'll talk about it in a little bit here. If all the chemicals, so again, this is a little bit, again, another addition. If we took everything in here and we dumped it in a vat, right? Some things, it looks like there's a lot of reactions happening at the same time, but not really. Some things are going to be predominant, and they're going to occur much more predominantly than others, okay? And for me, it all comes into focus when we start talking about, go full circle at the end of this and start talking about rust and sacrificial anodes. I think that's when it really comes in for me. But for now, we'll just have to realize, oh, some things are stronger oxidizing agents and reducing agents than others. So let's take a look at these tables and take a look at the chemistry of it. And that's what I mean when I say chemistry, oxidizing agents and reducing agents and stuff. But in any table of standard reduction potentials, reactants, Albert, are always being, so here's a table. I just copied and pasted it. The reactants are always being what? Reduced. Everybody agree? Okay, just pick one. Cu plus 2 goes to plus. Plus 4 goes to plus 2. And plus it's called standard reduction potential. So, all right. Okay. So the reactants are always what agents, Victoria? Oxidizing. Yep. Remember, oxidizing agents get reduced, reducing agents get oxidized. Okay. We're not quite done yet. I changed this. You have to fill in the blank. I'm just saying circle it. AJ, in this little table, circle the best oxidizing agent in that table. Circle the best oxidizing agent in the table. Now, agent is just another word for chemical. Okay, now his thinking is on track. It's got to, it's going to be an extreme. The only way I can figure this stuff out, yeah, it could be up here. Oxidizing agents always get what? Reduced. This is the only way I can figure this out. Oxidizing agents always get reduced, because I don't memorize jack. Oxidizing agents always get reduced. So, what in here is getting reduced? The reactants or the products? The reactants, right? So you have to pick one of these chemicals. You have to. Because those are the only guys getting reduced, right? These are all oxidizing agents. They're all getting reduced. So then you go back and say, oh, yeah, the ones with the most what E0 are the most aggressive, most positive. So you'd pick, definitely be looking at this half reaction, right? Because we're looking at the forward direction. So don't change sign or anything. The answer would be I2. You better circle him or write him in the blank. Okay. Let's place a box, Lauren, around the best reducing agent listed in the table. Would it be the CR? Right. That's what she says. You agree? Or is it this CR? All right. Reducing agents get oxidized. If you're going to pick something, you're going to guess, you better pick something that's getting oxidized. You have to pick something on this side. And they should do this, but they don't. Maybe it's a waste of paper. They standard oxidation potentials. Exact same table. Flip all the reactions. Change all the signs. So they don't, though, right? So we have to do that ourselves. Okay, this guy is getting oxidized. So he's a reducing agent. He's the most positive because we're talking about agents now. These are reactants. So he's the most positive, chromium solid. Draw a box or write him in the blank. Okay? Okay. Number 1 here. Order the following oxidizing agents by increasing strengths under standard state conditions. 1.0 molarity, 1 atmosphere, 25 degrees Celsius. Monica, what the heck? Is this just a Waste of space here or what? Why are they saying all this? Yeah, the table. You can't use, if you're not under standard state conditions, you can't use the table. So that's why they're saying all that. Okay. So we are supposed to order them, Mari, in order of increasing strengths, oxidizing agent strength. You have a game plan for this? Look in the table. Okay. She says look in the table. She's right, Eric. Let's pick this first one. Oxygen gas. What are you going to... He says 0.4. He wants to write... So my idea here, what I think you guys are talking about, is you're going to write a voltage next to each one of these. Right? And then we're going to say increasing strength, so least positive to most positive. And he's putting a 0.4 volts under the oxygen. Do you agree? Now, the only, he's right. I guess what I'm trying to say is I wish I would have picked a different one. Because some of these compounds, they're on both sides. Here, this case, you just find oxygen gas. Oh, there it is. Right? He's writing down the 0.4. So you're taking a couple chances by skipping a step. But I say the step is oxidizing agents get reduced. So you better be looking for this, the compounds on this side. All these compounds listed have to be on this side. In the homework, you're going to see, you're going to have to use that full-blown table. Some compounds are on both sides. Right? Now here, like tin. There's one. 10 plus 2. I should have had that in this list. I'm going to change that next time. Okay. So oxygen gas, it's on the right side. It's being reduced, positive 0.4 volts. What would you write down for cadmium, Ramiro? Cadmium plus 2. What voltage would you write down? Negative 0.4. Good deal. And sulfate. How about sulfate, Summer? Oh, sulfate shows up in 2 spots. That's a good one. Right? So are we going to looking at this one? Ah, she's right. It has to be reduced, so positive 0.2. Right? Well, positive 0.20 or 0.2. Right? Okay. Notice how, see how sulfate was in 2 spots? That was a good one. Okay. Now we have to order them in order of increasing strength. So which one would you list first, Alyssa? Increasing strength. Increasing. So the most powerful one, the most aggressive one, is the one that's the most positive. So list which one last? This guy last. First would be CD. Yeah. Okay. Cadmium, sulfate, and oxygen. So if you had all these guys in solution, right, all of them will react with electrons, but the one that's going to grab onto them first is going to be the oxygen, right? The other guys just, right, it's not going to happen. Consider the reducing agents. Oh, I'm losing my table here. Consider the reducing agents, copper, nickel, and iron. So go ahead. You've got the table. List them, or no, just pick which one's strongest and which one's weakest. All right, you've got the table. We want reducing agent strength. copper ion, nickel solid and iron solid. Albert, you get an answer? What'd you write down for, what voltage did you write down for copper ion? Negative 0.15. Everybody agree? Okay. See, reducing agents, everybody get oxidized. Everything getting oxidized are the products, right? So we got to find Cu plus on this side. Oh, yeah. Right? He's got it. He changed sign. There it was. How about the nickel solid, Victoria? What voltage did you put for that? Positive 0.25. Everybody agree? Good deal. And the iron solid, AJ? Negative 0.44. Everybody agree? Oh, you have to flip the sign though, right? Why do you have to flip the sign? Yeah, because these are supposed to be reactants, right? Remember that oxidizing agents, reducing agents are always reactants. They're causing it. He's the agent causing the other dude to get reduced. So these have to be reactants. The only way to make these reactants is to flip the sign. Okay, positive 0.44. So which one is the strongest reducing agent, Lauren? The Fe solid. Which one's the weakest? Everybody? Copper, copper 1. Okay. I think this leads us into rust, right? I mean, dang. Iron is a really strong reducing agent. That's not good. That means iron wants to get, right? Iron wants to go this way, right? Oh, I guess you write it this way. We're going to keep it this way, right? You have to flip the sign. So you have to imagine yourself, iron solid going to Fe plus 2. It really wants to happen. Positive 0.44. That's a strong reducing agent. Okay, here we go. See if we can put all this together. Iron rusts because of the half reaction marked with an arrow. And which other half reaction? So here's the first one. Okay. You have some oxygen dissolved in water, reacts with some electrons, if available, produce some hydroxides. Positive 0.4. Right? That wants to happen in that direction. Positive 0.4. What's the other half reaction, Monica? To explain rust. What would be the other half reaction? All right, so one of them is the has to involve this guy, right? If we wanted an overall reaction, an overall cell reaction, Mari, for rust, right? Which reaction would you flip? The red one or the purple one? Which one would you flip? The red arrow or the purple arrow? Right? Then we could cancel electrons, get the overall, what's that? The iron one, yeah, because he's negative. So you flip the iron one, you get a positive, what, 0.84 volts. That really wants to happen, and it does, right? I mean, whatever that rust thing is, it's happening. Okay. They pulled the guy out. Yeah, I'm sure they cleaned off all the little barnacles and stuff to get better gas mileage that way. But look what they slapped on there. Brand new sacrificial anodes. Okay. Here's the answer. Now, iron solid, then, is a pretty good what agent? Reducing agent, because he gets oxidized. He's a pretty good reducing agent. You got to find a better one. Find a more aggressive reducing agent. Slap him on the ship, iron's left alone until all that other aggressive material is gone. And then the iron will start reacting and you get rust to go on. Okay? Eric, what could it be? What's that? Aluminum? Okay. That would work, but the problem then is we're kind of messing with our, that's a good guess. We have water, it's almost like electrolysis then, I think. We can't go beyond this guy. Yeah, chromium would work, but what do you know about chromium? Yeah, you get chromium in the environment, it's not heavy metal, it's not good. But zinc? Don't you take zinc tablets, right? I mean, it's in magnesium. I mean, it's in those old men tablets I take every morning. It says zinc. So zinc. That's what they zinc coated or galvanized, right? That's what they're going to use. So they coat the iron or make these little ingots, zinc, and then what happens is this guy produces zinc plus 2 and all these electrons. Now you can't stop this one from happening, but the point is that, man, this guy produces all these electrons, iron Fe plus 2 reacts with them and it just stays that way. You can't really stop this guy from going that way, but you do because there's such an influx of electrons from this guy, he'll stay there. So this one is going to react all first. Once he's gone, then the iron solid will start. Okay? Okay. I'll have to go back and see why the heck that aluminum answer. Sister, you remember that? Why wouldn't aluminum work? The sacrificial anode.
No, I'm trying to remember. I don't remember. I'm sorry.
But I think the point is that you get water almost electrolysis. You know those guys that you pump in, you've seen this. I did this once. You set up these little electrodes and you plug it in the wall and you get oxygen bubbling up on one tube and hydrogen gas bubbling up on the other. So I think that's what goes on. You have electrolysis of water before you get these to go. So that isn't going to work. I think. I don't really remember. But Eric, I'll have to look that up. Okay.
But it's an easy answer because of the zinc and we know about it.
Yeah, I know zinc. All right. Oh, we already answered B. We're good, right? What is the standard cell potential? Okay, here's some homework questions that you can expect. What is the standard cell potential you would obtain from a cell at 25 degrees Celsius using an electrode in which iodide, that iodide anion, is in contact with iodine solid. Then you have a chromium strip, and it's in a chromium solution. What is the standard cell potential? Dang, Ramiro, we have all these equations. What variable are they after? They're after volts. That's the units, yeah. But what's the symbol in all these equations we have? Which variable? It's E0 cell. And you're right, Ramiro, it's volts. They're after E0 cell. To me, that guides all my efforts, and then I kind of read the rest of it to see what I need to find. So, Summer, what are you going to do to get this here? good. I like that. Let's create the half reactions. Or we could just start with what this equation is. Maybe you don't need the half reactions. What equations would we use to get E0 cell? Someone said was the easiest one. Yeah. It might be easier to see if you actually write out the half reactions, add them up, get an overall reaction. But it's extra work, but I think it might be easier to see what Summer was doing. Right? Each half reaction, get the number of volts for each one, add them up. And remember the game? You just have to add these up so you get the most positive. Okay. So see if you can identify the two half reactions. You could actually write them in if you'd like, but you really don't need to get the overall cell reaction. It's a lot of extra work, but it doesn't hurt anything. Maria, did you identify the two half reactions? The I2 one and the CR3 plus one, right? The very top one, the very bottom one. Albert, you remember this? Do we leave them alone? Do we have to flip them? What if you wanted, if it said get the overall cell reaction? Flip the most negative one, exactly. So you would flip the chromium one, right? It looks like you'd have to multiply the top one. Well, I guess you start writing some stuff down, right? You have the I2, and the I negative one, the chromium solid, chromium plus 3 one. And you got to multiply, I think the iodine one probably through by 3, this one by 2. But you don't really care, right? Because these cell potentials, they don't change. The iodine one is what number? The iodine half reaction. You would write down 0.53 volts. What would you write down for the chromium half reaction? Positive 0.74. So the answer would be, thank you, 1.27, right? Okay. And if they wanted the overall cell reaction, you could give it to them. You okay with that? What is the standard Gibbs free energy for the following reaction? Use data from a table standard reduction potential to solve. So there's, gave you the data. We're going to need some equations, right? Where'd it go? See it? Right? It's the only place it shows up. So that's where I would start. I would write him down, and then he guides all your efforts. Okay, Victoria, what do you want to do first? Find the two half reactions. Okay, which two would, let's write them out then. What would they be? Yeah, see how she's copying this? 2I goes to what? Goes to I2, solid. Okay. Well, it's right here. Right. Notice how I don't know if you realize this. If you just went through and started picking these out, wouldn't you pick this half reaction and then you'd pick the one with chlorine, right? You can't jump that high. You'd pick that one. See that one way up there? You got to be careful doing these because you have to do what Victoria started doing. You want to add up these half reactions so you get their reaction. That's what you have to add up. Whether you get the most positive E0 or not, it doesn't matter. You have to get their reaction because that's what you want delta G0 for. It may not be spontaneous. They may be interested in something else. So whatever you get here has to match, has to be identical to what's here. Okay, so she started out right. 2I minuses, not this way. Okay. Well, I guess you have to add, might as well finish it here. 2 E negatives. And what do I write down for my E0 for that? For this half reaction. Yeah, you got to flip it. Good. Negative 0.53 volts. So do the same for the next half reaction. Figure out what its voltage is. Add them up, get E0 cell. The second one is what? 1.36. Everybody agree with that? That's 0.83. Thank you very much, Summer. Okay. So we have E0 cell. Yeah, that F is always, I give it to you, 96,485. 485 coulombs per mole of electrons, right? Mr. Faraday's constant. Let's see. It has to be Cl2 going to Cl minus. So Cl2 is going to Cl minus, so leave it alone. Positive 1.36. Yeah, because this guy is Cl2 going to Cl minus. And how many electrons do we have in there? 2 electrons. So if we add everything up, it should work. What is my little n going to be? X, we have the F. Little n's going to be 2. It's the number of electrons that cancel. So my little n is going to be 2. All right. So you plug all that stuff in. And AJ, you don't want to lose a point for units. When you finally get an answer here, what units are you going to slap on that thing? Joules. In fact, probably joules per mole. Right? Okay. And why, you pretty much got to take some physics and find out what voltage times charge is. But it's joules. Okay. What'd you get? 1.6 times 10 to the 5th? Is that right? 1.6 times 10 to the 5th? Yeah, and it would be negative, right? Because they never got rid of that negative sign. Because negative NFE0. Negative 1.6 times 10 to the 5th. Monica, did you get that? We have about 1 minute left. Any problems with that? Okay. I don't think we can get through this, but we can set it up. Get the equilibrium constant. All right? So you have to hunt down the equilibrium constant expression. Right? Rearrange. Just kind of like what we did. Right? That problem's going to be a job. So you have to get E0 cell. Just add up the half reactions. What's N going to be again? Electrons that cancel. And just solve for your K. Right? Raise both sides to the 10 power. I think it's easier if you plug in all the numbers first. And simplify it before I raise everything to the 10 power. But so that's about it. We're out of time. So come by if you have some questions.